everyone. So today we are talking about energy. So again, this 14% of the exam, that was the old number. I'm not really sure on the new percentages, but it's going to be around there. Okay, so energy. Okay, property of matter that is manifest as a capacity to perform work. Okay, this guy right there, James Joule. Notice there is no vector sign. Energy is a scalar. The unit joule is the same thing as 1 Newton meter. Okay. So types of energy, we're just talking about mechanical energy. There are lots and lots of other types, but we just talk about mechanical. So mechanical is just the sum of kinetic plus potential. Now, kinetic energy is energy due to the motion of an object. Potential is the energy due to the object's position. So two main types of potential we talk about is spring. So it's stored in the compression or stretch of a spring. Now, did not bring my springs home with me. So best spring example is curly hair. Okay. Other example, gravitational. So it's stored in that gravitational field. Okay. I'm currently on the 9th floor of a building. So I have all of that gravitational potential energy. And then if we just add up all the kinetic and potential, we get total mechanical energy. So linear kinetic energy, that is our nice normal type. Okay. It's just 1/2 mv squared. This lady right here, Emily du Châtelet, she was the one to figure out that it was 1/2 mv squared for kinetic energy and not momentum. Newton thought it was momentum, but he was wrong. She fixed it. Okay. We also have rotational kinetic energy. Now it takes energy for objects to rotate, and that's 1/2 I omega squared. Okay. So if you have a bigger moment of inertia, it takes more energy to get it rolling. Okay. And it has less kinetic. Linear. So in this right here, the disk and the hoop, they both have the same amount of potential energy. Now, the one that's going to win is the one that takes less energy to rotate. So let's see if you remember which one wins. I'm not really sure why it's nice and intense like this. Okay. This music's a lot. They're still not going. There we go. Okay, so slow-mo, obviously. Okay, but the hoop is mr squared, and the disk is 1/2 mr squared. So because it's 1/2, it takes less energy to rotate, meaning it has more linear. Okay. Now, potential energy are two types. Okay, we have spring, 1/2 kx squared, where k is our spring constant and x is how much it's stretched or compressed. Now, simple harmonic motion is no longer on the AP exam, but spring potential energy might be. So keep that in mind. You still need to know what k is and what this formula is. Our other type is hidden by the little inset, but potential energy from gravity is just mgh, mass times acceleration due to gravity times height above the ground. Okay. Now, potential energy graphs. Okay, we did this a while back, but we just have to remember force is the negative derivative of potential energy. Okay, so the U of x is just a general potential energy function. We don't have to know what kind of potential energy. It could be any type of potential energy. Okay, we just use U as a placeholder. Now, negative derivative, meaning A. This derivative, okay, is negative, but the force is positive. Okay, and then between C and D, the derivative is positive, but that means my force is negative. Okay, so force is negative du dx. We do have 2 points of we have multiple points of equilibrium, stable and unstable. Okay, so stable is going to be C and E. Now, those are the points, okay, if you just push it a little, it's going to eventually come back to C or E. Now, unstable is something like D. If you have like a marble sitting there, you push it a little, it's never making it back to D. Okay, so it's unstable there. Now, this line right here, okay, is our total mechanical energy. You can never go above that line. So I can never make it to this hill right here or past A. Okay, I have to stay between A and G. Now, for these graphs, if you know what the total mechanical energy is, you can find kinetic energy by saying kinetic plus the potential, which you can just read off this graph, must equal total. And that's how you find kinetic energy of this function. Now, conservation of energy, EI equals EF. So what kind of energy do you have at the beginning? it equals the amount you have at the end. Okay, you probably are going to have some sort of question where EI equals EF at some point. Okay, so if two objects start with the same potential energy throughout, they have the exact same amount of energy. Okay, it's just different forms depending on how it's going on. Okay, so same amount, just different forms. Now, pendulum energy. Okay, my face is covering this picture, but you remember the guy with the bowling ball? Okay, he brought it up to his face, let it go, and it came back. It's never going to hit him because of conservation of energy. It would need more energy to be than it began with to reach his face, so he was safe. Okay, potential or pendulum energy problem. This is a very popular problem that they like to put on the AP test. So what you need to know is up here, if this is the beginning, it has potential energy of gravity, mgh. Okay, h is just this little distance right here. It is not the length of your string, it's just this distance. Okay, so here is our velocity is 0 because we have the maximum potential energy. It falls down. Okay, here is where it doesn't have any gravitational, all kinetic, and it's moving the fastest at the bottom. So to figure out the value of h, we know the length of the string must equal this total length. Okay, using some trig, we can say this part is L cosine theta. So therefore, your height is just L minus L cosine theta. Okay, if that is confusing to you, send me an email. I can work it out on paper and show it to you a little bit more. Okay. Okay, work. Okay, just an object's change in energy. Okay, now one of the graphs we have is force and displacement. Okay, force displacement, the integral is work. Okay, so you get f dx, which is fd cosine theta. So remember, this is a dot product. We have force, we have displacement, we dot them together and get a scalar. Okay, the difference between dot and cross products, you take two vectors, cross them, get a vector. Dot products, take two vectors, dot them, you get a scalar. Okay, so we did a work lab on this one, okay, with the bouncy ball, and then we had like the little poppy toy. Okay, that's work, change in energy, okay, due to a force with a displacement. Now, the force has to act parallel to my displacement. Okay, so if I'm holding something, I'm holding my phone, and I'm gonna walk forward. Okay, I don't do any work because the energy does not change. Okay, also another reason, the force here is up, the displacement is sideways, that angle is 90 degrees, and if we go back to our equation, cosine of 90 is 0, there's no work. So even though I'm moving it, I'm not doing any work, its potential energy is not changing, its kinetic energy is not changing, therefore there's no work. Okay, you do work to lift something up, but not to bring it sideways. Okay, now power. Okay, my friend Power has been super stressed lately. His boss is making him work overtime. Hey, okay, but remember that is only if the force and velocity are constant. If the force is not constant or the velocity is not constant, you cannot use that amazing joke, okay? Instead, you have to use calculus, okay? Do not be afraid to use calculus, okay? That is the biggest mistake that happens on the AP test is students don't use calculus when they're supposed to be. So power is the rate at which work is done. So it is the derivative of work with respect to time. If force and velocity, if force and velocity are constant, you get work over time, which ends up being force times velocity. Okay, but that is only if they're constant. Now we did a lab. Okay, here where I made you run up some stairs. Okay, you probably remember that. So keep that in mind. And power is measured in watts. So turn down for watt. Hey. Okay, that's Tesla, obviously. Okay, and if we were in school, this is the point where I would go make you run some stairs right now. Go ahead and do it if you want, but obviously I can't force you to run through stairs. So that's energy in a nutshell. The worksheet is attached. And remember, Friday there is no new assignment, okay, but I will be posting the answer to our trivia question. So have a great day, and let me know what questions you have.